Okay. Sometimes, guys, all you can do is just keep a positive attitude. It's not that big a deal. The only thing that sucks is, well, I guess we're pretty ahead. I could spend Friday as well on this if I feel like there's a lot of material we haven't gotten to. But for now, we're just going to spend today on it. But we have the luxury of spending a part of a part of Friday on 12.7 as well if I feel like we didn't get through too much. Okay, so in a volume, we're talking about triple integrals here. In a volume, we can get a little wedge of a volume, a tiny differential piece of that volume. Okay, and this cube is going to have a dx, a dy, and a dz, where dx, dy, dz is your delta volume. And then we can define a triple integral by saying the limit as L, M, and N approach infinity. I equal 1 to M, J equal 1 to N, K equal 1 to L of some function of 3 variables. This will equal the triple integral across some region B, okay, of some function dv. Let's just jump in by what we mean by that. A cube can be defined as a Cartesian product of 3 closed intervals. What do I mean by that? Some cube, some region B, in which we're doing a triple integral, can be defined as some AB cross some CD cross some RS. So then this guy is the same thing as the integral from R to S, integral from C to D, integral from A to B of some f of x, y, z, dx, dy, dz. So let's do an example. The actual integrating stuff is not what is difficult about this section. It is determining how to set up the integral. Pulling the integral off is typically, because you guys are so well trained at it by now, it's typically not that bad. It's setting up the integral that is more of the challenge. So let's say you want to know what is this right here. X, y, z squared b, and your region B. Let's say we want it to be 0, 1, cross -1, 2, cross 0 and 3. That becomes a 0, 3, -1, 2, 0, 1 of the function x, y, z squared. What came first is the dx, then the dy, then the dz. Then you just go about integrating this entity. I'll do the first iteration for you guys. 0 to 3, -1 to 2. This is an integral dx. So it thinks y's and z's are just constants. So this becomes yz squared. It thinks that's a constant. X squared over 2, evaluate at x is equal to 0 and x is equal to 1, dy dz. So, you know, this then equals integral from 0 to 3, integral from -1 to 2. y z squared times put a 2 when we factor out a 2. So it's 1 squared minus 0 squared dy dz. So then what's inside the bracket is just a 1. So this becomes integral 0 to 3, integral negative 1 to 2 of 1/2 yz squared dy dz. And you just carry forward. The x thinks it's a variable when there's a dx. The y thinks it's a variable when there's a dy. So eventually, you move forward and you integrate. What should we get when we're done? When we're done, you should get like a 27 over 4. What's more important is how do you set up these integrals? This integral is pretty straightforward because your boundary B is very explicit. Let's really talk about situations where the boundary B is not so easy to determine. That's like the more difficult portion of this section. Okay. So we have like 3 types of region. Here's type 1. So let's say you have a region like so. You have this kind of amorphous shape. And it casts this projection onto the xy coordinate. Let's call this the xy plane. Let's call the projection of the objects onto the xy plane some region D. And let's call the actual 3-dimensional surface some region E. Okay. Remember type 1 and type 2 regions and double integrals? Okay. So notice that, maybe we could integrate this thing if we had something bounding this bottom, some u1 equals some z, and some u2 equals some z. What if there was some function that determined the surface, its values, ranging from that bottom part on the z-axis all the way to the top part of that z-axis, where our u is actually going to be a function of x and y? How could we define the integral? Well, in double integrals, we recall that we can, for f of x, y, z, we can define some capital F of x, y, z, such that it's piecewise defined to be f of x, y, z if your x, y, z is an element of E, and 0 if x, y, z is not an element of E. I know that you may think that capital F stands for the antiderivative. It doesn't necessarily. I don't know why the book uses that script, but it does. So I'm just bringing it up to you that this doesn't mean antiderivative. It's just a new piecewise defined function. The reason why they do it is for theoretical purposes that is beyond the scope of this class. But just know that if you define that to be like that, then our region E can be defined to be the set of all x, y, z, such that if x and y is an element of D, then our U parameterizes the position of Z. So our U2 and our U1. Damn. Oh, close the brackets. Where, yeah, D, as I said, it's the projection onto the xy axis, or xy coordinate of E. The whole surface E projected onto the xy plane, and that's what D is. So in a type 1 region, what would the integral look like? Well, you get bound by E, f of x, y, z. It's going to equal, let's clear up some space here. Here's the cool part. We create from this triple integral a double integral integrating a single integral where this is from u1 of xy to u2 of xy of your function, what? dz. So how do we know that we can decompose in the type 1 region a triple integral into a double integral integrating a single integral? Is that I erased it, unfortunately, but that surface that I just erased, like this, here's D, here's E. Notice that this is the z-axis, right? And we were able to discover some function that parameterizes the values of this surface in 3 dimensions, all the way from the bottom of it at the lowest z equals value to the highest z equals value. So it depends on how is your 3-dimensional surface floating in 3 space. We'll see more examples here in a second. Okay. How am I doing on time? Okay. All right. What if you have your boundary, your projection region being type 1? Okay, what if you have a situation like this? So in these problems, you guys are gonna have to like create pictures and analyze how can I what kind of type of a situation do we have here? And that's the way you can set up the integral. So let's say this is your region D, this is your region E. Here's this projection onto the XY plane. Notice that, okay, here's the x-axis, here's the y, as usual. Notice that right here, we could say, oh, over here, this is some y. And maybe I can define what's going on here by saying, oh, y is some function of x. And over here, y is some function of x. Those are g's. And then again, we can still say that, okay, and we have some function for z, here's some u1 of xy, u2 of xy. Let's set up a triple integral. So its projection and its surface are what will be what we're interested in. And maybe we could say that over here, this is the point A, this is the point B, right, on the x. So the function can, the integral can decompose to integral from A to B. Integral from y is equal to g1 of x to g2 of x. Integral from z is equal to u1 of xy, u2 of xy. of your function f of x, y, z, dz, dy, dx. So the order in which you're integrating matters in these integrals. Based off of the kind of surface you have. Before, we didn't have any of this business going on. It was just this business. Now, this is required, so we changed the integral. Okay? Now let's talk about D being the type 2 region. Type 2. Okay, got an amorphous region here. Its projection is over here. Now, x, y, z. Here's another situation. What if this from here to here, if this is your C and this is your D, and clearly this is your y-axis. What if we said, okay, from here, my x can be represented as some h2 of y right here. And my x can be represented as some h1 of y. All the while, z is equal to u1 of xy, u2 of xy. How does this change our integral? Well, we notice that along the y now it has normal inputs, but along the x and the z, it's going to have those functional inputs. So this is going to be so first will come dz, next will come dx, last will come dy. How are we doing on time? Oh, wow. Guys, the power of positivity is real. It was like 7:55, and I was like still around Lake Hefner. And I was like doing calculations in my head, saying, okay, I know if I drive 70 miles per hour, I know I can get to class around start time. And it worked out, man. It worked. I didn't get pulled over. Ooh. You get lucky sometimes, you know. Do not drive that fast normally. But you guys are worth it. Your education is worth it. Okay, let's do an example. All right. What if we want to know the value of this triple integral? And we haven't defined this region E yet. Let's say E is created by planes x equals 0, y equals 0, z equals 0, and one last condition, x plus y plus z is equal to 1. For these problems, it is imperative you draw a picture. Imperative you draw a picture. Okay? Let us do that. X, y, z. So x equals 0 is the plane that goes through the y-z plane, right? And y equals 0 is the plane that goes through the xz plane. And z equals 0 is the plane that goes through the xy plane. So we got basically a plane here, and a plane here. And what joins them is this function. The thing that closes the fourth face of what will create a tetrahedron is this function. Notice that function, when we solve for z to get an expression only in x and y, we get that is 1 minus x minus y. So what we'll get, this is 1, 0, 0, 0, 1, 0, 0, 0, 1, and we get a solid tetrahedron connecting. So it's filled. And this will be our region E. How do we know that? Well, this slanty part right here is what closes the shape. It's that f of x, y is equal to 1 minus x minus y. It's a plane. How do we know it does that stuff? Well, this is a function of x and y, right? At x equals 0, on the xy plane, when x is equal to 0, you get 1 minus y, okay? And so you know that 1 minus y is when x is equal to 0. And that's why that forms this plane like so, right here, 1 minus y in 2 dimensions. You could call this like an x. Or you could see that that's a line equation. At the origin, it's equal to a 1. So you know that's why you get this point right here. And then this gives you, again, that's why you get a slanted line this way. So this 1 minus x is this slanted line this way. Then 1 minus y is this slanted line that way. So how am I relating a 3-dimensional shape to a 2-dimensional shape? I'll show you. And this is imperative to do. You guys have to draw the 3-dimensional region E. But we're also interested in knowing what is its 2-dimensional projection onto the xy plane. This triangle-looking thing, right? Indeed, it will be a triangle-looking thing, right? Where over here it's at 0, 1, and this is at 1, 0, and this slant from here to here. What is that given by? So your y is going to equal 1 minus x. Just like your x, I told you earlier, this is your x, would equal 1 minus y. Notice that in both cases, let's say I wanted, so if this is y, you get that again here. Just add a y and subtract the x. That's just the same thing. Right? Okay. So that's why I'm saying y is equal to 1 minus x. It's a line that has y-intercept 1, a slope -1, right? That's what's going on here, right here. From here to here, that's the x component, so I'll make it fuzzy, fuzzy. From here to here, it's the y component, I'll make it loopy, loopy. Well, they kind of both look loopy. You guys get the point. You guys have wonderful imaginations. Really, math is all about using your imagination. It is. It really is, isn't it? I mean, you're giggling and you're laughing, but it's true. We use our imaginations, but then we use critical thinking and logic and analysis. But really, the imagination portion cannot be understated, especially in Calc 3, where we start drawing lots of pictures and whatnot. I really like that part. I like using my imagination. Albert Einstein once said, while he was alive, that imagination is more important than knowledge. Knowledge just gets you to where everything else is at, but imagination allows you to travel the universe. Because although we're here restricted on Earth for now, our minds can go and imagine what it's like to be in different galaxies and near a black hole and near neutron stars that are as big as our planet, but they're spinning 300 times per second. It's hard to wrap your head around that because our planet spins once every 24 hours. They're spinning 300 times per second. There's neutron stars that spin that fast. It's really cool. Yeah. Okay. So notice that now we can integrate this region like so. Where down here, what is the parameter? And up here, what is the parameter? Well, down here, the parameter so up here, we already know the parameter is y is equal to 1 minus x. And over here, we already know the parameter, it's y is equal to 0. Okay. So now, let's write down what I just said. Y ranges from 0 to this 1 minus x. Wonderful. Step 1 out of 3. What does x range from? 0 to 1. What does z range from? We require this slant that comes out function. The z is equal to 1 minus x minus y. And so we know that because of that, can you guys see if I write here, down right here? Mm-hmm. Okay, I don't want you to have to crank your neck over there. So z then ranges from 1 minus x minus y to 0. There you go. So these ingredients right here, through analyzing the 2-dimensional shape and the 3-dimensional shape, allow us to define what our region E is in terms of parametrizing all the ranges of x, all the ranges of y, all the ranges of z. This allows us to build our triple integral. The building of the triple integral is the harder part than actually doing the integral. It's kind of like creating a car or writing some software. creating the software is a lot harder than playing the video game. Way harder. Yeah. So that's what we're doing right now. So triple integral e of z dv, because recall that's what we're always trying to solve, is now equal to, we have everything we need to know to solve it. What does it range from x, 0 to 1 for x? What does it range for y? 0 to 1 minus x for y. What does it range for z? 0 to 1 minus x minus y for z. And this is a z, dz, dy, dx. And the order does matter, the way we set it up. By that, I mean, if I wrote this integral first, I have to put the dz first. Fubini's theorem says that the order of integration does not matter overall, given Fubini's theorem's conditions. But if I wrote this, I can't write dx over here, because that's the parameter for z. And after that, you just integrate away. All right, so this becomes z squared over 2, evaluate at 1 minus x minus y, and 0, dy dx. Let's just pull out that 1/2. This ends up becoming 1 minus x minus y squared minus 0 squared dy dx. This ends up becoming a double integral from 0 to 1, from 0 to 1 minus x of 1/2 times 1 minus x minus y squared dy dx. Okay, you just keep going. Now you need to do u substitution. All right, let's do a u substitution. Let's let that 1 minus x minus y equal u. So then we know that integral from 0 to 1, integral from 0 to 1 minus x of 1/2 u squared. Now, what is our replacement for? I did du dx. I should have did du dy. Oh, well, thankfully, it still equals a -1. But this is a y, and this is a y. So this then becomes a negative du when I replace dy, and this becomes the dx. And I do the substitution for u. So this needs to go away right here. Just a second, integral 0 to 1. And then you just continue. Once you continue doing this process, the integral keeps churning out values, and you eventually get 1/24. What's most important is setting this integral up. Knowing what these limits of integration are is truly the quote-unquote hard part. Doing the integral is all about remaining focused and not messing up minus signs and not forgetting to distribute. You guys know how to integrate. That stuff is pretty standard at this point. It's the setting up this part. It's the drawing the pictures and analyzing what does this slant equal and what does that slant equal. So let's see how we're doing on time. Okay. Then this is wonderful. I can't believe it. I was able to get through all of lecture. Power of positivity. This morning I did not think I'd be in this position I am right now. Oh man. So let's now, we can't do any more like computations, but we can talk about the different kinds of regions that we have. Here's a type 2 region. Let's say you have something like this. We don't always have to project onto the XY. You can project on the YZ. Okay? You just then have to modify your integration right here. Notice that this will be some x is equal to u2 of yz. Some x is equal to u1 of yz. And you go about your merry way. A different situation is a type 3. The projection actually is not even restricted to YZ. It could also be XZ. So here's the region B. Here's region E. And this, your Y1, will be a function U1 of X and Z. Your Y2 will be a U2, a function of X and Z. And you'll form integrals with respect to these situations. So let's say that, like, you know, for example, this is C and D. All right. And you get it, you get that point. The Z would probably be parameterized some way. Given some parameterization for Z. Clearly, if it forms like a cylinder emanating in the X direction, you know how to define something like that. It'd be like a some Z is equal to X squared plus Y squared, but that would be if it was like, you know, right in the center. So you're gonna have to have some like shift. Z is equal to some X minus some shift in the horizontal, and Y minus some shift in the vertical squared, quantity squared. So for type 1, our E, I deleted type 3, but type 1, our E could be like the set of all X, Y, Z, such that Y and Z are in D, and U1, YZ, so this one would correlate to A, B, A. And similarly for type 3. So setting up the integrals here is harder than the actual integrals. Although you may get a situation where the integral is also hard. Setting up is hard and the integral is also hard. Why would the integral be hard? Well, it's probably because you need to shift to polar coordinates, or maybe you need to shift to spherical coordinates. If the integral is very difficult in rectangular coordinates, you might think of utilizing the symmetry of the situation and using polar coordinates or spherical coordinates. Like with these tubes, polar coordinates would be very helpful. And with things that have circular or spherical symmetry, you might want to go for a polar or a spherical coordinates. But actually, in the next section, we'll be talking about cylindrical coordinates. So that will help us deal with cylinders right away. Okay. I will give you guys back some more graded work. That's really all the announcements I have so far. Keep up the wonderful work, everybody.